All right. So today kind of brings together our two concepts of delta H and delta S, our enthalpy and our entropy. For this entire unit, we've been talking about how we can calculate enthalpy. And as chemists, we are very interested in the amount of energy that is released or absorbed during a chemical reaction. Yesterday, I introduced you to a term called entropy, which is a measure of how disordered a system is. It's also a measure of how much actual work a chemical system can do. And I say a measure because it's actually a combination of the delta H and the S. But this is a good enough introduction for you guys. When you encounter this topic in university, you'll get a more deeper explanation, which is fine. I don't have nearly enough time to actually go into the depths that need to be done to truly explain it, but it's good enough. Entropy is a measure of how disordered a system is, and it's also kind of a measure of how much work it can actually do, all right, like pushing a piston or moving something. What we want to do now today is talk about what makes a chemical reaction spontaneous. And we've never really talked about that before. We've just kind of assumed it. If you put chemicals together in a reaction vessel, either the reaction can proceed and a reaction happens, or the reaction cannot proceed. It just sits there. It doesn't do anything. We've seen successful and failed reactions before. We've seen them in single displacement reactions. You put together the right metal with the right compound, and if you use the activity series, you can then determine whether that particular reaction will take place or not, whether it goes on its own, whether it's spontaneous. But if you have a different metal that is already alone, that wants to be alone, we know that that reaction won't take place. We would call that a non-spontaneous reaction. It just doesn't happen. And so what we want to talk about now is what determines whether a reaction will be spontaneous or whether it won't happen and be non-spontaneous. All right? And we have the tools now to make those predictions for any chemical reaction. As long as we have our thermodynamic data, we can make those predictions. Let's first define a spontaneous reaction. What a great statement. Reactants become products. Well, of course they do. That's what a chemical reaction does. So it seems kind of silly that we have to define it, but I guess the first one is the most important part. It occurs without continuous outside interference under a given set of conditions. An example of a spontaneous reaction, and this one will come up in this discussion, could be H2 gas, like in the hydrogen balloon, with some oxygen gas, all right, to produce some H2O, and we'll put it as a gas in this case. And I think I need a 1/2 in here to balance that up. Now, if I put a little spark, and by putting a spark, that's not continuous outside interference, that's an initiating bit of energy. We'll talk about that later. That's different. The spark is needed to get the reaction initiated, but once the spark is there, I don't have to continually add heat to that reaction. It feeds itself, and the hydrogen burns, and the hydrogen balloon explodes. So that's not continuous outside interference. Given the right conditions, hydrogen and oxygen will combine to form water, and it will do it all on its own. That is spontaneous. All right? Non-spontaneous reactions. It doesn't occur without outside interference. Seems pretty obvious. reactants do not become products. And a non-spontaneous reaction example is just the opposite of what I used as my example for spontaneous. Right now in the air in this room, there's water vapor, right? There's some humidity. That's water vapor. That means that in the air right now, there is H2O gas. And that H2O gas is not spontaneously breaking down into H2 gas and O2 gas. It's just not happening, all right? Even if I put that spark, right? If I had my lighter, I've lost my lighter. I need to find my lighter again. We'll do the thumb lighter. Even if I had a lighter and held it out in the air for all that water vapor, that's not going to take place, all right? We can make that reaction happen under certain conditions, but I need continuous energy input. If I were to put the water into a Huffman apparatus, which you might have seen in grade 9 and grade 10, and we put the electrodes in there and we plug it into an electrical device and we input electrical energy, we must continuously input electrical energy to rip those atoms apart. So we can force it to go, but without outside interference, it won't go. We call that a non-spontaneous reaction. All right? We can come up with physical examples of spontaneous and non-spontaneous. You have a rock on the side of a hill, you let it go, it rolls down the hill all by itself. That's a spontaneous physics or physical interaction. It rolls down the hill. Rocks roll downhill. Pretty straightforward statement. They don't just roll uphill on their own, but you can get them to roll uphill. You just need some continuous outside interference, someone who wants to put in the effort to roll the rock back up the hill, but they don't spontaneously roll uphill. This is a similar idea. Certain reactions happen on their own, and other reactions don't. They need some help. We want to be able to predict what makes one spontaneous and one not spontaneous. You don't write this down. This is just examples of some spontaneous reactions. Like I said, if we have a single displacement reaction, all right, check the activity series. Silver wants to be on its own. Yes, it takes place all on its own. No effort needed. Silver with some copper chloride. Silver wants to be alone. It is alone. That reaction doesn't happen. It's non-spontaneous. So we have all kinds of examples of spontaneous and non-spontaneous reactions. You can write this down. So what makes a chemical reaction spontaneous? Well, there's two reasons. There's two factors, and it involves enthalpy, delta H, and entropy, delta S. The first one we'll talk about is the enthalpy, which is essentially that energy that's stored in a chemical reaction. I've already given you one reason why a reaction happens spontaneously, and it comes down to the statement, rocks roll downhill. It always happens. In terms of gravitational potential energy, an object that has high gravitational potential energy will always eventually move to a position where it has lower gravitational potential energy. Asteroids fall from the sky, rocks roll downhill, what goes up must come down. Those are all examples of objects moving to lowest energy, lowest potential energy. That's true for a chemical reaction as well. Remember, enthalpy is kind of like a measurement of the stored energy in a chemical system. It's the energy in the bonds. It's potential energy. And so just like in a physical system, something of high gravitational potential energy will just naturally proceed to lower gravitational potential energy. A chemical system of high enthalpy will naturally proceed to a system of lower enthalpy. And when we have a system going from high enthalpy to low enthalpy, we say it's a negative delta H. We say it's exothermic. Exothermic reactions tend to be spontaneous. And notice I said tend, because there is a second factor that affects this. Chemical systems react to minimum enthalpy. Rocks roll downhill. It's the same thing. The universe, for some reason, whoever designed it, it's going down a theological path. I'll stop. Whoever designed the universe has it built into the universe that things of high potential energy naturally settle down to situations of low potential energy. Rocks roll downhill. Fundamental law of the universe. And we see it everywhere. So if we have a chemical reaction that has a negative delta H, it's exothermic, then it has the potential to be spontaneous. Now I've got a next slide here that illustrates this, not illustrates it, but kind of fortifies it. I'm just, thinking ahead to where I want to be at the end of class. I don't think it's necessary to write this next slide down. Let's just take a look at it, and we'll be critical about it, and then and decide whether it's important to write it down or not. This is the important part here. Chemical systems react to minimize the enthalpy. Delta H's that are negative, the universe likes. The universe drives that reaction forward. So this next slide here, I've got here, chemical systems naturally proceed to minimum enthalpy. I think we've expressed that. A reaction is spontaneous if the enthalpy of the system decreases, if the delta H is negative, so high enthalpy to low enthalpy. A reaction is non-spontaneous if the system increases in enthalpy. In other words, a positive delta H, and there's my does not proceed. I think we get that idea. I don't think we need to write that down. If a reaction is exothermic, the universe likes it. It has the potential for being spontaneous. So let's just move on to the next part of the idea, and that is the law of entropy. We've seen entropy. It's a measure of disorder. It's a measure of how, disorder, chaos is a word we sometimes use, chaotic, disordered, a chemical system is. And it turns out that chemical systems naturally proceed from a state of order to disorder. And I had a statement for the entropy slide that you wrote that I think said chemical systems proceed to a state of minimum enthalpy, or they decrease the enthalpy. And so I'll add that same statement to the bottom here for entropy. Chemical systems proceed to a state of maximum entropy. All right? So if a chemical reaction can have a delta S that's positive, for some reason the universe likes that. Yesterday I went on a tangent how scientists believe, or they theorize, that our perception of time is based on this law, on how we perceive things going from ordered state to disordered state. And then I went on a crazy tangent about all points in time existing simultaneously. It's very intriguing. If you want to continue that discussion, come at lunch. Mr. Petrus disagrees with me over many campfire discussions. So two laws that govern spontaneity. Minimum enthalpy, negative delta H, maximum entropy, positive delta S. And we know how to calculate both. So that's where we're at. We're simply going to be doing some examples now where we calculate the delta S and calculate the delta H, and we make a decision. Is this got the requirements for spontaneity, or does it not? And as you can imagine, there's going to be three type of situations we can have. We can have the enthalpy go down and the entropy go up, spontaneous. We can have the opposite, the entropy go up and the enthalpy go down, non-spontaneous. The universe doesn't like that. But then we've got two intermediate situations. The enthalpy goes up, universe doesn't like that, and the entropy goes up. Oh, the universe likes that. And then we've got this competing situation, or down and down. And those middle guys, those ones that are either up and down, have the ability to be spontaneous at one temperature, but not spontaneous at another temperature. So there's this switchover temperature where spontaneity can take over. So those are the situations we want to discuss. So, very simple thing you keep in your mind, those two laws right there. Again, in chemistry, we like to have little tiny sayings that help us get through. What did we have last year? Did we have any silly little sayings? Did I go over any of them? At the end, well, for electrochemistry, we have oil rig, right? But we haven't learned that one yet. I'm trying to think. Did we have a silly saying? Yeah. Oh yeah, ikai high, so low. Excellent. It's a good one. Ikai high, so low. And this one here, minimum enthalpy, maximum entropy. The universe likes reactions to have move to minimum enthalpy, negative delta H, and move to maximum entropy. Most chaotic system. All right. Let's look at some examples. Hold on, don't write this down. We're going to actually, hold on, let me see what I want you to write. Yeah, I do want you to write the top part, but don't write the examples. Don't write the examples. Just write the top part. A reaction will always be spontaneous in the forward direction if it is exothermic with increasing entropy. So here I've got a quick little table. If I put my enthalpy, and I put here at positive and negative, and my entropy as positive and negative, we can then kind of find the spots where we're going to have spontaneous reactions or non-spontaneous reactions. All right? So in this case, positive delta H greater than 0, negative delta H and positive delta S. If the delta H is negative, that's spontaneous. And if the delta S is positive, that's spontaneous. So this is always spontaneous. So this is always spontaneous. All right? If we were to maybe put check marks where the universe likes it, the universe likes this, but the universe doesn't like that. And the universe likes this because it likes chaos, but the universe does not like that. So the universe likes this and likes this, always spontaneous. All right? Some of you may even like this idea better than even writing all this stuff down, right? This is a little more graphic of a representation. If we need a legend, right? I don't want to put spontaneous, but the universe likes this, right? I don't even want to maybe touch that, right? Because spontaneity depends on both. I can't just say check mark is spontaneous. I could say check mark is spontaneous with respect to that particular thing, like the delta H or the delta S, but that's getting way too much, way too wordy. So in this case, a reaction will be non-spontaneous in the forward reaction if it is endothermic and the entropy is dropping, it becomes more ordered. So those are my X's. X and X. This guy is always non-spawn. Always non-spawn. I'll be using that term over and over again when we start doing some examples. And that's fine. You don't have to write spontaneous, because I don't know how anybody really knows how to spell spontaneous. All those vowels in there, E's and O's, and goodness, there might be a U in there. Sometimes I stick an I in there. It's chaos. A lot of entropy in my spelling. So let's just go with non-spawn. Look, I put the T in there. Always spawn. Don't even worry about the T. Okay, that brings us to the other two situations. And I can bring the next slide up. I know we're looking at two things at the same time. Again, let's not worry about these examples. But we say a reaction is reversible if the delta H and the delta S have the same sign. And that's because the universe is pushing them in opposite directions. One reaction is spontaneous, and then the other one is non-spontaneous. It's actually driving it in the opposite direction. So when we have a plus and a minus, right, so like we have here, the delta S is pushing it in the forward direction, the delta H is pushing it in the opposite direction, and that's reversible. And I hate reversible as well. Reversible. It's reversible. I've trained you well. There's very little laughing going on. So when you have this situation, like I said, in this case, the delta S is pushing it forward, but the positive delta H, the endothermic, is actually pushing it back in the other direction. And we've got competing reactions pushing in opposite directions. Okay? In a non-spontaneous reaction, we really have both effects pushing it towards the reactants, and so it doesn't do anything because they're being pushed towards the reactants, according to the universe. Always spontaneous is being both pushed towards the product, but with reversible, one part is pushing it towards the reactants and the other part is pushing it towards the products. So you have this continual switch back and forth between reactants and products. That's why we call it reversible. It can actually head either way. And we have the same situation here. This guy is favorable towards delta H, not favorable towards delta S, also reversible. And look, I even forgot an S in there. That's why you guys are giggling at me. Still spelt it wrong. Scribble, scribble. Also reversible. Okay? I kind of quickly went over the examples to get it to be written down, but all I have here are situations where, notice, negative, right, is the delta H. This is also less than 0 because I'm going to a more ordered state. So this is exothermic, but it's also being ordered. The universe is pushing those in opposite direction. The universe wants chaos, but wants the minimum amount of energy. So it's being pushed in opposite directions. In this case, it's endothermic. So the universe doesn't like to proceed this way. It wants to proceed back this way. And in this case here, it is got an entropy greater than 0 because it's becoming more chaotic. So it's pushing it the other way. Again, that one is reversible. All right, even though I use it as an example of non-reversible. Anyway.